welcome to Chapter 16, Acid-Base Equilibria, Part 3, where we're going to discuss relationships between Ka and B, acid-base properties of salt solutions, acid-base behavior and chemical structures, and Lewis acid and bases. So the relationship between Ka and Kb, we kind of talked about this a little bit already, but if you multiply the two, so Ka times Kb will give you Kw. So for conjugate acid pairs, you have your Ka and Kb are related in such wise. And this is important. You could only multiply Ka and Kb to get Kw if they are conjugate acid-base pairs. If they are just two random acids and bases, you can't multiply them to get Kw. But if you know one, then you could calculate the other. Also notice that as the strength of the acid increases, the strength of the base decreases. So as Ka goes up, Kb goes down, or vice versa. So your conjugate base, say your acid has a relatively high Ka, then your conjugate base will have a relatively low Kb. So some acid-base properties of salts. So now, in the past, we've always discussed that you mix an acid and a base, you make salt and water, and salts were kind of considered as neutral, but that is not necessarily the case. So many ions will react with water to create H plus or OH minus ions, and this reaction with water is called hydrolysis. To determine whether a salt is acidic or a base, you need to look at the cation and anion separately. The cation can be acidic or neutral, and the anion can be acidic, basic, or neutral. So reactions with anions and water. So remember, anions are negative. Anions are bases. As such, they can be written as a reaction with water or hydrolysis to form OH. So here you have your anion plus water. You're going to form some acid plus OH minus. What will affect an anion's ability to react in such a way? Well, anions of strong acids will result in being neutral. Okay. For example, chlorine ion or chloride will not react with water, so OH minus can't be formed. So if your anion is the conjugate base of a strong acid, then your anion is neutral. Now, if your anion is the conjugate base of a weak acid, then they will create OH in water. Okay? Because if your acid was weak, what does that tell you about your conjugate base? Your conjugate base is stronger. So it will react. Remember, your reaction will always move from the stronger side to the weaker side. Okay? And protonated anions from polyprotic acids, so remember acids that have more than one H in them, they can be acidic or basic. It depends on the Ka value. If your Ka is greater than your Kb, then the anion is acidic. If your Kb is greater than your Ka, then it's basic. So let's talk about cations now. If your cation is a group 1 or 2 metals, then they are neutral. Okay? Because if you were to basically add an OH to those, you would see that they would give you your strong bases. So they're the conjugate of the strong bases, sort of. Polyatomic cations are typically the conjugate acids of a weak base. So, for example, NH4. Okay, so transition and post-transition metal cations are acidic. Why? There are no hydrogen atoms in these cations. So when we're talking about transition metals, right? What about hydrated cations? Transition and post-transition metals form hydrated cations. The water attached to the metal is more acidic than free water, thus making the hydrated ions acidic. So here we have iron hydrated. It has a bunch of waters attached to it. And what happens is these waters here kind of react with this tail that's sticking off here. And it makes this bond here more polar. Because all of this part of the molecule here is more negative, so it's drawing the electrons more over here. So then it's making this bond and this bond more polar, which then allows this hydrogen to be pulled away and donated to the water, making this acidic. So here is a close-up example, okay? Cations with acidic protons, like NH4, will lower the pH of a solution, okay? Most metal cations that are hydrated in solution also lower the pH of the solution. The attraction between non-bonding electrons on the oxygen, so, you know, your lone pairs here, and the metal cause a shift in the electron density in water. So here we have our electron pairs. So these electrons are highly attracted to this positive charge, thus making the OH bonds here even more polar, making it easier for these hydrogens to, this bond to break, and this hydrogen to be released and donated, okay? This makes the OH bond more polar and the water more acidic. The greater the charge and the smaller the size of the cation, the more acidic. So this one here is more acidic than this one here. The effects of cations and anions. So an anion that is the conjugate base of a strong acid will not affect the pH. It will not. So you have to look at the anion and say, oh, what acid pairs up with this? If the acid that pairs up with that anion is a strong acid, it will have no effect on the pH. An anion that is the conjugate base of a weak acid will increase the pH, so it'll make it more basic. So you look at the anion and you say, oh, what is the acid that pairs up with it? If it's a weak acid, then the resulting solution will be more basic. A cation that has a conjugate acid of a weak base will decrease the pH or make it more acidic. So you look at the cation, you add OH to it, you ask yourself, is this a weak base or a strong base? If it's a weak base, then you're going to end up with a more acidic solution. Cations of strong areneous bases will not affect the pH. So any of your strong bases, cations that go with it, will not affect the pH at all. So just keep it neutral. Other metal ions will cause a decrease in the pH, making it more acidic. And these are your transition metals, aluminum, higher charged metals, not your group 1 and 2 metals. When a solution contains both the conjugate base of a weak acid and the conjugate acid of a weak base, the effect on the pH will depend on Ka and Kb. If Ka is greater than Kb, it will be acidic. If Kb is greater than Ka, it will be basic. So again, group 1 and 2 metal cations with anions of a solid acid will result in neutral. No change in the pH. Group 1 and 2 metal cations with an anion of a weak acid will end up in a basic solution. Your transitional or post-transitional metal cations or polyatomic cations with anions of a strong acid will end up acidic. and your transitional or post-transitional metal cations or polyatomic cations with an anion of a weak acid, you have to compare your Ka and your Kb. So let's try these and see what we get. So the first thing you want to look at is each ion separately. So this one here, we have Ba and CH3COO minus. Barium is a group 2 metal, so it will not have any effect. But this here is acetate, and acetate is the conjugate base of acetic acid, which is a weak acid. So this is the conjugate base of a weak acid. And if you remember correctly, if your base is the conjugate base of a weak acid, then it will make the solution basic. Okay, let's look at NH4 and Cl minus. Cl minus is the conjugate base of HCl. HCl is a strong acid, it will have no effect. NH4 is the conjugate acid of a weak base. So your solution will become more acidic. Let's look at KNO3. K plus is a group 1 metal, so it has no effect. NO3 is the conjugate base of nitric acid, which is a strong acid, so here you will be neutral. Let's look at Al. ClO4 minus. ClO4 minus is the conjugate base of a strong acid. It has no effect. Here we have a highly charged smaller metal ion, and that will result in a more acidic solution because it will make the OH bond in water weaker, allowing the hydrogen to donate, and you will end up with a more acidic solution. So factors that affect the acid strength. There are 3 factors. 1, the polarity of the bond between the hydrogen and the anion. So the HA bond here must be polarized with a delta positive on the hydrogen and a delta negative on the other atom. The strength of the bond. The weaker the bond, weaker bonds can be broken more easily, making the acid stronger. So if you have a binary acid and the bond holding the two together is fairly weak, it will be a strong acid. Because remember, the definition of a strong acid is a substance that ionizes completely. And in order to ionize, you have to break the bonds. The stability of the conjugate base. So here is your conjugate base. The more stable your anion means the stronger the acid. So factors affecting acid strength. First of all, there's a couple trends. As you go down a group, your acid strength will get stronger. And as you go from left to right, it'll also get stronger. So acidity increases from left to right across a row and from top to bottom down a group. Why is this? Well, let's just look at binary acids first. Binary acids consist of hydrogen with one other element. So here we have some binary acids here. Within the group, that hydrogen to whatever the atom is, bond strength is generally the most important factor. So within the group, we're going to look at bond strength. As we go down the group, the length of your bond gets longer. If the length of your bond is longer, the strength of the bond is weaker. The weaker the bond, the stronger the acid. So the weaker the bond, the stronger the acid. Longer bonds are weaker. So as you go down, the atoms are getting larger, so you have longer bonds. So that is why as you go down a group, you are becoming a stronger acid. Within a period, going across this way, it depends on polarity. So as you move from left to right, this element here is becoming more electronegative. The more electronegative it is, the more polar your bond is, the easier it is to break that bond, the stronger the acid. We also have another type of acid called oxyacids. They consist of hydrogen and oxygen and one other element, which is a nonmetal. Generally, as the electronegativity of the nonmetal increases, the acidity increases. More polar, the OH bond will allow water to attract the H plus away from the OH, making it a stronger acid. So here, this is electronegative, pulling the electrons there, making this bond very polar, then making this hydrogen easier to be lost and donated. If you're donating, you're an acid, okay? In oxyacids, in which the OH bond to another atom Y, this will be our Y here, the more electronegative Y is, the more acidic the acid, because the more polar this is, the easier it is to take this hydrogen and donate it. So oxyacids with the same other element. So here we have 4 oxyacids, and as you notice, as you move across, you're getting more oxygens. The more oxygens you have, the more acidic your acid. Why is that? Because the more oxygens you have, the greater the electron density over here is, pulling the electrons closer to the oxygen, making this bond here more polar. So as you're going across here, your OH bond, let me just write that here, is more polar. So it is easier to break. If it's easier to break, you could donate this hydrogen, making the acid, making it more acidic. There's a special type of acid called carboxylic acids. They are organic acids containing the COOH group. So factors contributing to the acidic behavior of these groups. Other oxygens attached to the carbon will draw the electron density from the OH bond, increasing the polarity. So here we have an oxygen bonded to carbon, so it will, oh sorry, this is for the bases. And its conjugate base, the carboxylic anion, has a resonance form to stabilize the anion. Resonance in conjugate bases of carboxylics stabilize the base and make the conjugate acid more acidic. The last thing we're going to talk about, and we already talked about this at the beginning of the chapter, we'll just review again, are Lewis acids and base. Lewis acids are electron pair acceptors. A Lewis base is an electron pair donator, or donors. All Bronsted-Lowry acids are also Lewis acids and bases. There are compounds that do not meet the Bronsted-Lowry definition that do meet the Lewis. So not all Lewis acids and bases are Bronsted-Lowry acids and bases. So here's a good diagram here. Here we have these two compounds that need to bond. So remember, your electron pair donor, donating, is the base. The substance accepting it is the acid. Your Lewis acids are defined as an electron pair acceptor. In order to accept this pair, your atoms must have an empty valence orbital. See here, there's an empty valence orbital. It's an incomplete octet here. So it could be a Lewis acid. Lewis bases are defined as electron pair donors. Anything that could be a Bronsted-Lowry base is a Lewis base. Lewis bases can interact with things other than protons, however. Lewis acids and bases also help explain the whole metal cation effect that we talked about earlier. The hydrated metal cations are primary example of electron pair donor or acceptor chemistry. The higher charges result in stronger water to metal bonds. So see here, this attraction here is greater, making them stronger acids. Lewis also explains how metal cations can form acidic solutions since they are strong electron pair acceptors from the oxygen atom in the water molecule. And that is the end of part 3.